Welcome to this in-depth exploration of JAX's just-in-time compilation. We'll start with the basic setup process and then move into more complex concepts. To begin, we need to install the JAX library in a Colab notebook environment. JAX is very versatile when it comes to different runtime environments, and in this demonstration, we'll be working with the TPU, or Tensor Processing Unit, runtime. After connecting to the TPU, we'll complete the JAX TPU installation process. Once we have our environment set up, we'll examine primitives and JAX expressions to better understand the compiler concepts. Let's begin with our first example. After creating an initial function, we'll use something called makeJAXPR to generate and examine a JAX expression. This gives us a JAX expression that has been simplified into a sequence of primitive operations. In our example, we can observe two logarithm operations and a divide operation. An important design feature to note is that you won't see any side effects in these expressions. JAX's transformations are specifically designed to work with functionally pure code, which means code without side effects. We want to avoid impure functions because they can be dangerous in several ways. When writing our code, we should eliminate side effects and ensure we're working with pure functions. Let's understand how JAX handles this through tracing. When JAX processes a function, it wraps each argument, in our example we're using an argument called x, with something called a tracer object. These tracers are responsible for recording all the JAX operations that happen during the function call, which takes place in regular Python. After recording these operations, JAX uses the tracer records to rebuild the entire function. What we see as the JAX expression is the result of this reconstruction process. Because tracers don't record Python side effects, these side effects don't appear in the final JAX expression. To better understand side effects, let's look at another example. If we add a print statement like print x to our code, it won't change our JAX expression at all. The JAX expression stays exactly the same because printing text is a side effect and isn't functionally pure. JAX handles this internally by creating a separate traced version of x. Another crucial concept to understand is how tracing works with conditional code. Since tracing only happens one time, we need to be especially careful when working with conditions in our code. Let's explore why this matters with a specific example. For example, let's explore what happens when we return different values based on whether x has a rank of 2 or not. With a rank 1 input, the function simply returns x. But with a rank 2 input, the processing path changes completely. This difference in behavior based on conditions can cause issues. To handle conditional logic more effectively, we need to use alternative approaches. Let's introduce the CLU function as an example of how to properly handle conditional logic in JAX. Instead of using traditional if-else statements, we use a where expression that's represented as a Boolean condition. This condition checks whether our input is greater than 0. The function captures all the dynamic behavior using an if B then A else C structure, and then multiplies the result by 1.05. This approach gives us a proper sequence of primitive operations that can handle conditional logic correctly. This careful handling of conditionals is essential because it allows JAX to maintain its functional purity while still supporting conditional operations. The result is a function that can be properly traced and transformed, unlike the problematic conditional code we saw earlier. Now that we understand how JAX handles tracing and conditional logic, let's see how this knowledge applies to the just-in-time compiler. We'll use our CLU function as an example and evaluate it at approximately 1 million points to demonstrate the importance of optimization. When timing these operations, there's an important technical detail to remember. We must use the block until ready function. This is necessary because we're working with asynchronous operations. Without this function, we would only be measuring how long it takes to send the computation to the TPU, not how long it takes to actually complete the computation. In our initial approach, we're sending operations to the accelerator one at a time. This method significantly limits the XLA compiler's ability to optimize our function effectively. What we really want is to give the XLA compiler access to as much code as possible at once, allowing it to perform full optimization. This is where the just-in-time or JIT transformation comes in. While the just-in-time piece is a bit of a misnomer, the compilation happens at runtime, sort of like an interpreter. Let's walk through what happens when we create a JIT-compiled version of our CLU function. First, we pre-compile the function. Then we run the same workload we ran before, but this time with our optimized version. The results show a significant improvement. The processing time is notably lower with the just-in-time compiled function. The process works like this. The JAX expression we created earlier for our CLU function gets compiled by XLA into highly efficient code that's optimized specifically for our TPU. When we make a call to the function, this optimized code runs. An important efficiency gain comes from subsequent calls to this just-in-time compiled function. They use the compiled code directly, completely bypassing the Python implementation. Now that we understand how just-in-time compilation works successfully, let's deliberately examine some common mistakes to understand what not to do. The first issue involves conditional code that isn't properly structured for JAX. When we try to just-in-time compile a function with traditional Python conditionals, we'll encounter an error. This relates back to our earlier discussion about how JAX needs to handle conditional logic in a specific way. The second problematic case involves using runtime variables to control the flow of our function. For example, if we create a function that uses a runtime variable in a while loop, we'll run into similar issues. The fundamental problem here is that we're trying to control the function's flow in a way that prevents proper compilation. JAX cannot compile these types of functions ahead of time, a priori, because the flow control depends on runtime values. Fortunately, we can fix both of these issues using two different approaches. For the first case with conditional logic, we return to the solution we discussed earlier with the CLU function, using JAX's where construct. This allows us to express our conditional logic in a way that JAX can properly compile. For the second case involving runtime variables, we need to explicitly tell JAX to use a less abstract tracer for specific inputs to our function. We accomplish this by importing the partial function from the functools module and specifying what's called a static argument in our example. This tells JAX exactly how to handle these variables, and while it somewhat constrains the optimizations, at least we can still use JIT in these cases. However, there's a subtle point to be aware of. In the demonstration, we end up attempting to just-in-time compile these functions twice because we've already used decorators in previous steps. This isn't exactly what we want, and it's important to be mindful of how we structure our compilation steps. If you'd like to support the channel, consider starting a free trial of our new design tool, which is linked in the description, and let us know what you think. We'll include a link to the JAX documentation in the description as well. If you have any questions, please post them in the comment section, and we'll do our very best to respond. Thank you very much for watching to the end, and please enjoy responsibly.